thanks everyone for coming out today. And Em and I are going to do this a little bit of a tag team. I'm going to speak for a while and then hand off to Em. And then we want to do this as interactively as possible. So I think we can see you can ask questions in the question Q&A function, or stop, or we'll certainly have time at the end for questions and answers. So I'm Larry Jacobs. I have a faculty member in mechanical engineering and civil and environmental engineering. And Em, she can introduce herself. Do you want to quick introduce yourself, Em?
Sure, I'll go ahead. Hi, everyone. Thank you so much for coming out today. My name is Emmeline Evans, and I'm a second-year PhD student in mechanical engineering at Tech, and I'm co-advised by Dr. Jacobs and by Dr. Stebner, who just joined the webinar. Dr. Jacobs, you've still muted yourself. Oh,
Sorry.
there we go.
God, I told you I was an idiot with this stuff. Okay, sorry. I muted myself when you were talking, and then I couldn't unmute. Okay, let's go back here. And okay, so at a high level, again, we're going to talk again, give you a sense of what we're doing at Georgia Tech with this AI manufacturing pilot facility. And then we've broken the talk up into two pieces. One piece would be more traditional non-destructive evaluation, looking at post-manufacturing inspection. We're going to just highlight two different techniques, ultrasound and radiography. And then we're going to actually one of the application to a number of advanced materials, so some additive, some high temperature materials. And then again, I think some of the stuff you all are very interested in, how do we use these technologies for process monitoring? And we'll talk about some thermal imaging and then some acoustic emission. So the ultrasound will be an active technique where we ping actively ping the specimen with ultrasound while and listen for what comes back. And acoustic emission is a passive technique where we sort of listen and then interpret the signals. And we'll talk about advantages and disadvantages. So we're going to start with a movie on the overall project that Georgia Tech is working on.
It's time to start building up, building back, and building better. Right here in Georgia, we're working to transform communities through projects that will kickstart job growth and through the development of new technologies that will not only enhance America's global competitiveness, but also create a more robust economy long term. Our focus is the intersection of manufacturing, artificial intelligence, and innovations that drive economic development. This project is called the Georgia Artificial Intelligence Manufacturing Corridor, also known as Georgia AIM. With partners across the state, this corridor will bring together rural communities and urban ecosystems, Georgia's diverse universities and technical colleges. And together, we'll activate AI technology to ensure the resiliency of America's manufacturing sector from future shocks and global competition. Georgia AIM will revolutionize the industry economies of Georgia and the nation through the equitable development and deployment of talent and innovation in artificial intelligence. And that's for manufacturing sectors from energy and aerospace and flooring to food production. Georgia AIM will take on supply chain challenges and prove that disruptive AI manufacturing innovations can forever transform our country's industrial economy for the better. We'll support incubators to empower ideas from people that haven't always been brought to the table. Diverse communities will see the benefits of Georgia AIM, specifically underserved Black and Brown urban communities and rural Georgia communities of all demographics, as well as active military and veterans, women, and people without a college degree. Our programs will reach every corner of the state of Georgia, from the biggest cities to the smallest towns. Education is also a key component for Georgia AIM, starting with students K through 12 and all the way through college. This will help us meet a critical business need to provide the highly skilled workforce and advanced technical training for the manufacturing jobs of today and tomorrow, especially as they relate to artificial intelligence. The AI manufacturing pilot facility at Georgia Tech will provide Georgia AIM and the nation with world-leading proving grounds for industry, government, and university partners to pilot trials and innovation of new technologies that will advance AI manufacturing and transition industry practices to new, exciting, and efficient ways of working. Collectively, Georgia AIM projects will develop the upskilled talent and high-tech innovations necessary for AI manufacturing to move our state and America forward. Innovating faster and stronger will not only create jobs, but will keep jobs right here in America. We're ready to build back better with the power of artificial intelligence.
Okay, so
It's time.
wait, okay, so I hope that all get you a sense of the overall aim of this program. We're a very small piece of it. And so, but it's a very large statewide with multiple universities and multiple approaches. I think it's important to think of this advancing of the application of new and modern technologies, artificial intelligence, and you see things like additive manufacturing, precision machining, robotics. Today, we're going to talk about non-destructive evaluation, non-destructive inspection. We can look at it in the QA, QC realm. We're following up, and if you didn't get a chance to see it, I know there's a recording of it on the site. My colleague Chris Saldana did a really nice video. That's the bar that we have to at least meet on augmented and virtual reality, and so he really gave a sense of what's going on, bringing in the factory floor. And all of these, I want you to see, Georgia Tech is doing research in the underlying technology and then also in the application side of things. You see the key for the overall project, and in red there, the number terms we're looking to scale up and translate, where we have a demonstration facility, and you see a couple pictures of that demonstration facilities to the right. It's just off campus on 14th Street. It's 20,000 square feet. It's configurable, so it's really an exciting place. And then also the most important thing is on training and upskilling. I mean, this is where how do we make sure the workforce can use all these technologies and are ready to do the kind of things that we want them to do. So in the non-destructive evaluation range, you see this just gives you a sense of our team. That's me there with the tie, and my colleague Jin Young Kim, Dr. Kim, who's a senior research engineer. You see M down the second from the right on the lower. And then we have a number of other graduate students. We have Fiona, Kashev, and Nate all working in the lab. There are multiple folks working in these particular areas. And we can start talking about now the two different opportunities, or the two ways we're going to break this talk up. The first one is on post-manufacturing. So let's say we've manufactured a part and we want to know, is that part ready to go? Can we say, yes, that part is qualified, but after the manufacturing process? And then so we'll look at a number of different techniques. As I said, we'll tend to look at some of the more acoustic-based techniques. We have two very different parts here. We have one is a high temperature composite. And then on the right-hand side, we're also going to talk about techniques that we can do active interactions as part of the process monitoring. So it certainly becomes very important in the additive space where, can we change things? Can we monitor as things are going along and make sure we can make changes in that particular part or in that particular process before it's too late and before the part is manufactured. So first, we're going to start with the post-manufacturing inspection. And I have a couple of slides that are going to get a little bit technical, so I'm going to apologize. But I really want to make sure that you all see that it's important that, I want to stress the quantitative aspects of what we're doing versus the qualitative aspects of what's available out there, and the kinds of applications we want for the in situ monitoring or for the complicated parts that we're looking at to be able to answer the kinds of questions we want to answer It has to be, we have to have an understanding of the underlying, let's say, the acoustics of a wave propagating through. And again, in my mind, when I teach a course like this, I like to talk to or use the analogy to medical ultrasound. So if you've had an echocardiogram, this is why I have atrial fibrillation, and I use the same technology, an ultrasound with an array technology, to basically measure the ejection fraction of my heart, and then my cardiologist can interpret that signal. We're taking the same kind of technology here, that same kind of ultrasound where the ultrasonic waves do the work. But what you'll see is on this big plot here, on the vertical axis, we're going to have a length scale. So let's say for an additive part, we're going to be oftentimes very interested in things that are happening at the nanoscale. And we're talking about dislocations or precipitates, very much of the metallurgy or the microstructure of the part. And then otherwise, we'll have things at a scale up. Let's say if we're looking for porosity, or let's say we're looking for some kind of micro cracks that might have occurred, or some kind of voids. That's another length scale up. And then finally, at the largest scale, we have macro cracks. We have cracks on the millimeter length scale that again are, I'm going to call, relatively easy to find. I mean, that's the more typical technique. And what we're trying to do is develop techniques that can push down on that vertical axis lower and lower. So if we could have an understanding of what's happening at the dislocation level, right, it would be very helpful for us in things like using a term like a digital twin. Okay, that's very important in, let's say, the jet engine technology, where you can build a computational model of the actual component that you want. But as part of that manufacturing process, you have to understand exactly, what the state of dislocation or precipitants were. So the kind of work we're doing from a research perspective is driving lower and lower in the length scale to be able to understand better, or do better and better to understand how a part will behave throughout a complicated fatigue life with thermal stresses and things like that. So again, I'm sorry. I apologize for you bringing back any bad memories. And again, this is, if you just want to sit and think happy thoughts for a minute, you can. But what we have here is basically what's called a stress-strain relationship on the left-hand side. It's a constitutive relationship where we say the stress, which is, let's say, the load on a specimen, versus the strain. That's one is the sigma and the other is the epsilon, and the strain would be the material's response. And typically it's in terms of a number of mechanical or material properties that you can measure. And then typically we would talk about measuring the stiffness of a part, and that would be what you would use for linear ultrasound. And that's when, and if I use that echocardiogram example I gave, they understand again the stiffness if I wanted to measure, or they understand the properties of the body. What we want to do, though, in something, let's say, monitoring and let's say an additive, we want to go smaller. We want to go, again, let's say at the dislocation level. And a dislocation is a little mechanical precursor, let's say, to plasticity or some kind of damage, or even micro porosity, very, very small porosity. You see that becomes related to the wavelength, okay? Or basically in ultrasound, you have to think about it. If you want to find a feature that's, let's say, a millimeter, in length, you need to have a wavelength of the ultrasonic wave about at that wavelength. And so in a typical additive part, that is about 5 megahertz, which is a relatively high frequency for the kinds of parts we're looking at. And what I mean by that is the part where the ultrasound will scatter or will be very complicated, and it will be difficult to make the interpretation of it. And if we wanted to get smaller than a millimeter, a tenth of a millimeter, again, we have to scale up. So we have to go 50 megahertz, which is really hard to penetrate for these types of parts. So what we're doing is we're doing a combination. If you look at it, we want to look at what we're calling these ultrasonic fingerprints. So think about, you can identify different people or different features by their fingerprints. We're looking for those, and that's a combination of some kind of materials modeling. So you'll do, and I've just given some examples here of microstructural models on microplasticity and dislocations and some kind of, harmonic and harmonic features, right? And then, but also be able to measure things. And you'll see that when we talk about acoustic emission. Oftentimes, we know we can measure something, but we want to be able to relate what we measure back to something that's important to us. And so for us, we tend to look at those in the right-hand side, those 3 words that have very distinct meaning to us. Sensitivity. Is the technique, are the ultrasonic waves, or are the X-rays sensitive to the thing that we look for? Selectivity. Is it only sensitive to the thing that we're trying to find it with, right? Oftentimes, ultrasound is sensitive to a lot of different things. So we want to somehow, hone in on a particular thing that we're looking for, particular, let's say, microcracks or porosity. And so we have to take advantage or maybe of a multi-physics technique. And then uniqueness. Okay, we want to be basically everything we're trying to do, from, again, trying to go after these digital twins. We want to be able to predict the future or predict how things are going to happen in the future. So the uniqueness piece becomes very important. So now I'm just going to show you some highlights of the kinds of physics, or depending upon the material, the geometry, or the defect that we're looking for, we'll use different techniques. And so this would be, and again, this is a laboratory setup, but there are commercial type setups where this would be a non-contact type approach, where you see the sample there in the middle, where a tech could pull this kind of sample off of the line and put it in some kind of fixture. And in this case, we're using a non-contact acoustic horn. We're basically looking at like a trumpet, but backwards, and then some kind of, in this case, an optical receiver. This is a vibrometer. So in this case, we can look at, this is what's called NRUS, or nonlinear resonant ultrasound spectroscopy. We can look at very specific things, changes in features or thermal techniques, and this works for a wide range of very tricky materials. In the same way, we could go to a higher frequency, and this is a similar setup with a similar kind of material, and this is a high temperature, kind of material. This is probably, I believe this is a brake pad from, a carbon brake pad from, let's say, a race car type application, where we're now, rather than using acoustic, air coupled ultrasound at a relatively low frequency, we're using a much higher frequency ultrasound. And we're also perturbing the system. We're hitting at it, and we're creating another signal. So what we get in that is an image like this. And remember, I was saying, if you look at the medical ultrasound one, where you need either technician, a relatively well-trained technician to interpret, or your cardiologist to interpret. In this case, we're saying, okay, we get an output like this. This is something in the frequency domain, and this is for a slightly different technique. This is a second harmonic generation, and we'll take a look at some examples of this in a minute with an application to additive. But we can get pull data off of a plot like this and get a quantitative measure of something. So this next one is again, work that we did with Sandia National Laboratory. So we're looking at advanced additive manufacturing of some kind of stainless steels, a variety of stainless steels. And you see things like print rate, or cooling rate, manufacturing, method or bulk properties. We want to basically be able to vary, or oftentimes things will happen or will have some kind of problems with it. And again, oftentimes the sort of thing we can relate it all back to is this dislocation density. And that affects, the dislocation density affects a number of very important properties that we want, the ductility or the strength or the electrical properties. And so now we're trying to say, okay, how do we, in a relatively expensive part with the application to go real time, use these nonlinear ultrasonic techniques to do some kind of post manufacturing qualification. So we did, again, at Sandia National Lab, we used two different additive techniques, one a powder bed fusion and the other a lens technique. And you see we did, these are stainless steels, a 316 and a 304. And we compared to both the additive and the wrought, so the more traditional ones. And then we said, are we sensitive, or is this nonlinear ultrasound sensitive to the kinds of dislocations we have? And then so what you can see in a plot like this, and this is a lot of data, you see for 4 different parts, we have a 316 additive with powder bed fusion, we have a 304 additive with lens, and then we have the corresponding wrought parts, the more traditional. And you see we can basically back out this nonlinear parameter that we can measure. That's a beta. As we change the microstructure, in this case, we change the microstructure with heat. So if you see in the upper right-hand corner, the color code, we see the as received, or we heat it at 923 K for a half an hour, or a higher temperature at a half an hour, or a still higher temperature at half an hour. And you can see the kinds of changes you can make, right? You can measure in that beta parameter, which is an indirect measure of the dislocations. And then, so this is the sensitivity question. We're saying, is the parameter we're using sensitive to the thing we want? And in this case, yes. And then, so here, then we needed some kind of complementary technique. And in this case, that complementary technique was in this case, it's some kind of an advanced, density manufacturing, an advanced density mapping. It's a EBSD. It's an expensive technique. It's done on the surface with a lot of prep. But from this set of images here, an expert, and these are each of the parts at different times, and you see the as forged after the different temperature, and you see we're backing out 2 different parameters. And here we're looking at the lens versus the additive versus the wrought. And from this, we can make some kind of interpretation with it. I think the last one for me, Em, if you're ready, do you want me to do this one? And then I'll hand off to you. You see, again, we're currently, again, as part of the center, as part of this research project, we're looking at these high temperature composites, which are very difficult material to deal with. They're very expensive, and they tend to have a lot of flaws. So we're playing with, and this is Kashev is playing with these immersion techniques with ultrasound, and then we're trying to compare that to work that we do with, on the right-hand side, you see these Hertzian dry contact cones, which would be much more effective for a more practical application. So, Em, I'm going to go to the next one. Are you ready?
Sure, I'll take it off from here. I will have to ask you to advance through the slides though, as we go.
Absolutely. And Megan, maybe can you mute me just in case so I don't get any feedback, but I'm ready, Em.
All right, sounds good. Hi everyone again. I'll reintroduce myself. My name is Emmeline Evans. I'm a graduate student. I work with Dr. Jacobs and with Dr. Stebner on sort of a couple different sides of non-destructive evaluation research. And I'm going to sort of pick up where Dr. Jacobs left off when we're talking about post-manufacturing inspection. So we've heard a lot about ultrasound so far, and the techniques that we work on in the lab, some of them are very experimental. Some of them are much closer to things that are already deployed in industry and are ready for use in various applications. So, but a big part of our research is trying to close the gap between these more experimental ultrasound techniques and what's already commercially available. And so we need to have ground truth data to be able to compare what we get out of our ultrasound experiments against. And for a lot of the research that we're doing specifically with our high temperature composites, that ground truth data comes in the form of X-ray computed tomography. I work on these composites with my research partner, Keshav Bhatt, who is unable to be with us today, but he's also part of the non-destructive evaluation lab and a part of Dr. Stebner's lab, the BEAM team. So here, what we see on the slide are two of the machines that we have available to us at Tech. The one on the left is the Zeiss Metronome 800. That's the one that I use the most frequently when dealing with our composite samples. The one on the right is a VisiConsult. This one is much larger. This is much closer to something that you would see in a like commercial application. These machines can be used to scan much larger components, as you'll see in a photograph a little bit down the road. But this is what's essentially already out there and available, and we're leveraging this to help further our own research. So if you could move to the next slide, please. Like I mentioned before, this is already commercially available, and depending on the system, your part, its geometry, and the material, you can get you can accommodate parts from very, very small to very, very large. Most of what we work with are these small samples. They're usually about 1 centimeter by 1 centimeter, or up to 1 inch by 1 inch, sort of at the largest in cross section, and then in varying lengths. But you can also put vehicle components in some of these larger systems. Your resolution might not be as fine, but you'll still be able to see inside the part and be able to image defects. So if you can move to the next slide. Like I mentioned before, your resolution can really vary. The image that you see on the left is from one of our high temperature composites. That's actually from the F1 car brake pad, as Dr. Jacobs was mentioning earlier, where with either 2D or 3D X-ray computed tomography, we can image defects in the material that are on the scale of tens of microns in length. You can see the little call out bubbles showing either brighter streaks in the material or those dark spots. The darker spots in this image represent lower density areas. So they are cracks or air-filled pores. And being able to see these both before and after they are either used in like an application setting or damaged to or bent and tested on to induce damage that we can try to track through some of these experiments. Or we can image these before and after heat treatment to see how all of these different environments contribute to the degradation of a part. We also use this for examining parts post-manufacturing to see if they are up to the specifications, essentially. So this is something, the X-ray is something that is already extensively used with composites because they do pose more of a challenge to ultrasound inspection, but that's where some of our work is looking to close the gap. And be able to inspect these composite parts much in the way that we would inspect metals, particularly the AM metals that Dr. Jacobs was talking about earlier. And even the most sort of common and well-known applications of ultrasound inspection already are for use in detecting cracks in pipelines, like for oil pipelines, and also investigating structural damage and doing some structural health monitoring for applications, a lot of which are in infrastructure, like looking at bridge damage. And fire damage to bridges, things like that, things that are alarmingly topical these days with the collapse of I-95 in Philadelphia. But we're looking, like Dr. Jacobs has mentioned, we're scaling this down to manufacturable parts in our lab and then also in commercial settings. So if you go to the next slide, please. This is a bit of a sampler of what we use X-ray computed tomography or 2D X-ray to look at. in and around the AIMPF. So on the left, we have a sample of a additively manufactured molybdenum wall that came off our Optimec system, which we're going to talk about a little bit more in a little bit. In the center, again, we've got a 3D rendering or a 3D reconstruction of one of our ceramic matrix composite pieces, one of those brake pad samples. And then on the right, we recently in the BEAM team assisted a visiting professor with a project where he was looking to image AM nylon composites that were being used as a coupler or an adapter with a robotic arm. So we can really look at anything from these extremely dense refractory metals to these very, very light, very sort of porous, additively manufactured nylon composites, and be able to get a lot of great information about them and see where defects are, to see where the print patterns, and we can see the hatch patterns in them as well. So this is just like a very, this is a very commonly used technique for us, and it's also very widely applicable. If you could go to the next slide, please. So the last thing that we're going to talk about is process monitoring, and I'm going to frame this in the context of examples of things that we're currently working on at the AIMPF, particularly with some of our additive manufacturing research. A lot of this is us leveraging already commercially available equipment for our research purposes. Some of it is us also developing sensor systems based on research that is done in other groups and on our own experience. So there's a little bit of a flavor of everything in terms of the scale of technology readiness coming up in the next couple slides. If you could go to the next slide, please. Just an example really quickly, this is a video of our Optimec LENS system printing. So when we are printing a part here, this is with powder blown laser directed energy deposition. There's a lot that is going on in this machine. So you can see the print bed's moving, the powder is blowing out the nozzle. We have the laser melting the powder onto the substrate pool. This is it's a very loud machine. You cannot look at this without eye protection. It is extremely bright. It gets extremely hot. So there are so many factors in play and so many factors at play that could have potential issues going on with them. So we want to be able to track these manufacturing processes as well as we possibly can so that we can optimize parameters for both our research and for transitioning to industry applications. So if we could go to the next slide, please. One of the ways that we are looking into doing this is by imaging the melt pool in this machine, the Optimec, which again, I'm going to talk about a little bit more in a second, using infrared cameras. So we can actually monitor the melt pool as we are printing to be able to get a better look at the thermal gradient of the melt pool so that we can better predict where there may be defects being introduced in the part, such as porosity and poor layer adhesion. So we can see things like incomplete melting and incomplete fusion between layers. We can see where keyhole porosity may be developing by looking at these infrared camera images. If you go to the next slide, please. And like I mentioned, we're working on incorporating this into our Optimec LENS, which is laser engineered net shaping system, which is in the AIMPF. There's a photograph of it on the right. On the left is an example of one of the types of cameras that we're going to be integrating into the system, which is from FLIR. It's an X6980 series camera. What's great about these cameras and the newer ones that are on the market is that they are very high speed and they have very high frame rates. So we can really in real time image the melt pool and be able to see where defects may be getting introduced. And of course, these cameras are built to withstand those extreme build chamber environments. They get to very high temperatures with the powder flying around as the excess powder is blown out of the nozzles. We can go to the next slide, please. Another thing that we're looking at is, as Dr. Jacobs alluded to earlier, using acoustic emission techniques to monitor powder flow rates through the powder tubes in the Optimec. So one of the challenges of making sure that we are optimizing printing parameters for the various alloys, some of which are more experimental than others that we're working on, is making sure that the nominal values that we are inputting into the machine or asking the machine to do for us actually match what the output is. So when we are trying to control a powder mass flow rate through the powder tube while printing, what we can control is the RPM of the augers that essentially push the powder into the carrier gas flow and then through the flow tube out the nozzle. But we don't have a good idea necessarily just based off of that RPM of what our mass flow is all the time through the tube, whether it's consistent or whether there are gaps. We know that there have to be some, that it's not going to be perfect all the time, but we want to be able to monitor it, because especially when we're transitioning these technologies and even these types of sensors out into commercial industry, it's of no help to anyone if we say, okay, we know on our Optimec that we need to set this at some certain RPM, and good luck to everybody else figure out what that means to be applied to your system. It's much more helpful to everybody else if we can publish and say, okay, we know that this mass flow rate with this scanning speed and this laser power, this is what's actually going to create the best part. So one of the ways that we're doing that is monitoring this powder flow rate through acoustic emission. So the sensor setup that we're basing our sensor setup off of was developed by Justin Whiting out of NIST and published in the Additive Manufacturing Journal in 2018. And essentially the grand idea of what's going on here is that we can capture the powder particle collisions with the inside walls of the powder line tube as it flows from the powder hopper through tubing and then out the nozzle to be printed by recording the acoustic emissions, or essentially the noises that happen when those powder particles are colliding with the inside of the tube. So the energy of those collisions, or the intensity then of the AE signal or the acoustic emission signal, can be correlated to the mass flow through the tube, both in terms of velocity and the velocity of the flow and the total mass of the powder particles flowing through the powder line. Next slide, please. So just sort of to give you a better idea where this would be mounted, this is a photograph of some of the powder hoppers and the powder flow lines on the Optimec system from the back. So you can see we print with a couple different, or at any given time, we could be printing with one of a couple different types of alloys. A lot of these are refractory alloys or experimental refractory alloys that we switch between. So we want to be able to monitor the powder flow for a couple different types of alloys, which presents its own challenges especially when looking at what the best different methods should be for doing this, because not all of the powder particles are going to be the same size, especially across the different types of metals. So developing a technique that can be more easily applied to different types of powders and in different situations is going to be more helpful for us and more helpful sort of for the industry moving forward. Next slide, please. So here on the left, you can see a CAD model of the acoustic emission sensor and sensor mount that we're working on. And then also on the right, that is a prototype of the sensor and sensor mount. And I would like to thank Dr. Zachary Brunson, James Sangarides, Bhairav Ramanathan, and Daniel Palacios at the AIMPF for their work on this and for their help in preparing for and putting together this little section of the presentation. If you go to the next slide, please. One of the other things that we're working on that's related not to ultrasound nor to X-ray in terms of powder flow monitoring is capacitance sensing. So the main idea behind this is that the capacitance of a capacitive sensor is dependent on the dielectric constant of the material that's between the plates. So essentially, as the makeup of whatever is happening between plates of a capacitor changes, then the capacitance is going to change, and we can measure that capacitive change. So as the powder flow rate changes, there is going to be more or less powder compared to the amount of carrier gas in between these two plates of a sensor. So we can tell as the capacitance changes that the powder flow is also changing. Next slide, please. So on the left, this is a CAD model of the powder flow line capacitance sensor that's being worked on at the AIMPF. That effort is also being led by Dr. Zachary Brunson. And on the right, we have the completed prototype for one of those sensors. We're currently iterating through different designs for this capacitive sensor. At least one has already been tested. Sort of the second one is up in line to see what design is going to work best for us and what design is going to minimize noise and maximize essentially the strength of the signal. But this is currently ongoing and is something that's already online in the Optimec at the AIMPF. Next slide, please. That kind of concludes our presentation. I'll let Dr. Jacobs give a few closing comments as well, and then we're open to questions.
There. Okay, can you hear me now? Am I unmuted? Hi.
Yep, we can hear you.
Oh, great. Thank you. And thanks, Em. It was really, you did a wonderful job. And I hope you all get a sense again of our overall approach. Again, if I think back to that original slide where how do we translate the kind of research that we're doing and the kinds of applications we're looking at are the really difficult applications, whether it's material or where expensive parts or complicated parts, and then being able to get information, again, going to that AI piece of this project where like a digital twin, where you, again, take a lot of data and then somehow predict how a part will perform. In that manufacturing process, we're going to be providing the input data to know what the as-built information is. And so you see both of our emails there, and happy to answer any questions that way. And are there any, Megan, can you see, are there any questions in the Q&A?
Not as of right now. If anyone does have any questions, please feel free to use the Q&A feature, and we'll read those off and answer any questions you may have.
I see someone's on the phone.
Yeah, that's just them calling in.
Gotcha.
Yeah. Mm-hmm.
Gotcha. I can stop sharing. I can,
You can do whatever. If you want to stop sharing your screen, or we can leave that up. And just to let everyone know, I will be sending out a thank you email. I will include a recording of this webinar. And then I can also include the webinar that we had last month that Dr. Chris Saldana also presented, so that you can kind of refer back to what he presented about for the mixed reality on the manufacturing floor. And then any other additional resources that Dr. Jacobs wants to share, I'll be sure to include those as well. Let's see. We've got one question that just popped up.
Oh, good.
All right. So what is best method to test DMLS manufactured AM parts?
Can you tell me what DMLS is?
Yeah, it's just the acronym. So if we could find out, if someone could share with us what DMLS is.
Emmeline, do you know?
Are you talking about laser sintering?
Yes.
Yeah,
direct metal laser sintering parts. Yes. Mm-hmm.
So again, and I'm assuming, so the first question is, what are we looking for? And I would say typically for there, we're looking at porosity, and also, are you interested in distribution of mechanical properties? Are you looking for things like residual stresses? So would you want to go down to the dislocation, or are you looking for macro types flaws? And those would be the kinds of questions, sort of what are you looking for at what length scale? Okay, so for the nonlinear, for the dislocations or residual stresses, again, X-rays will do it, and then nonlinear ultrasound will do it also. But nonlinear ultrasound, X-ray there are commercial systems available, as Em showed, right? And that's that would be the state of the art. And then any kind of work with nonlinear ultrasound will also be. But it's still, I say the technology readiness level of nonlinear ultrasound, you see, we're still in, working, again, with like a national labs and looking to transfer it that way. So you come on.
Yeah. I would say, I guess the other, some of the other factors that I guess a choice of method would depend on is what kind or what data type, what output data type are you looking to be working with? So if you're looking at, if you want to be imaging pores or defects, then looking at X-ray more would be if this is a post-manufacturing inspection, looking at XCT or even just like 2D radiography is probably your better bet. But if you're looking for something that's more like you're okay with working with sort of like ultrasound data outputs, maybe doing some amount of that manipulation yourself, then you're looking more at the techniques that we're developing in nonlinear ultrasound. But also there are commercially available products and techniques out there for doing ultrasound imaging, not just medical imaging. So if it's something that's on the macro scale that's large enough to be detected by linear ultrasound, you could also find a commercially available like ultrasound probe or ultrasound like phased array setup that would allow you to image that kind of defect in real time. That's the kind of thing that's used for structural health monitoring on like the pipelines and the bridges that we were mentioning earlier. That's already widely available and deployed in a variety of industries.
And I would second what M's last statement about the power of phased arrays to be able to scan and to be able to answer those questions. And so, you probably, depending on the size, you could probably get a commercially available phased array for that.
Yeah, if you have like specific questions for about like a given part geometry that you're looking at or type of defect, please feel free to email and reach out to me, and I'd be happy to discuss it in more detail with you.
I think there's a follow-up question in there where it says the metal component manufactured with the DMLS was warped due to high residual stresses. And again, the situation is to localize the buffer material and then start machining. And so again, residual stresses obviously goes back to your dislocations question. If you saw those went back very earlier, we were using, dependent upon how complicated the part is, there are these resonant techniques that can allow you to get the overall properties and then dig in from there. Now these are a problem like this is really tricky and really difficult, and there's not a single silver bullet out there. And I would say this one would be, I would say, some kind of combination as I would use some kind of X-ray with something, with ultrasound. And it would depend upon the size. And then do you have a sense localized where it is in that complicated part? And then how well do you know everything else? Because the resonant techniques, you need information on, let's say, the bulk linear properties, to be able to use in a model. Yeah. That right. Can you see that? They say for now, I just used the 3D scanning and compared to the CAD model to locate the buffer material, started machining, but felt like it was not an appropriate method. Off the top of my head, again, it depends. My first question: how expensive is this part? And then, is it going to be? Do you have a lot of them? Is it something that you expect to see over and over? And then, if that's the case, you could get something a little bit better.
I think it might also depend on where, I guess it would depend also on like the geometry of the part and where this buffer material is. If it would be something that would lend itself well to like a surface wave type of experiment, like a Rayleigh wave experiment. If you're trying to localize, or if you're trying to find the areas of high residual stress, and if it's somewhere on the surface, doing a nonlinear Rayleigh wave experiment would help you find that. But I'm not sure in the part, like where in the part and what this geometry looks like, if that would be easy to set up or efficient to set up.
Yeah, nonlinear Rayleigh waves, and you think, as Em said, they were surface waves, and you can think of their penetration depth at about a single wavelength. So if you're depending on the kind of material, you can go a couple of millimeters in if you go a relatively low frequency, or you could localize it closer to the surface. But you can, and there are techniques to scan through frequencies and things like that. But this is a tricky problem.
All right. I don't see any additional questions unless anyone has any more. Feel free to ask them now. Also, I'll share their emails too. So if you want to reach out to them directly, you can do that as well.
Thanks, Megan. That would be great.
Mhm. All right. Well, if no one has any other questions, we can wrap it up and y'all can have 7 minutes of your time back.
Okay.
Yeah. So thank you all for joining us today. Again, if you have any questions, I'll provide their emails so you can reach out to them. And yeah, that's it. I'm going to go ahead and stop the recording.